He has 40 years of experience in the oil and gas exploration and development industry and leads many true oil finder groups in Egypt, Sudan, Syria, and Yemen. He is a teaching professor at the American University in Cairo, Ain Shemesh, Alexandria, and Cairo universities. Dr. Brucker will be presenting today on the he has 40 years of experience in the oil and gas exploration and development industry and leads
unsupervised
many
machine
true oil
learning for
finder
3D
groups in
seismic.
Egypt, Sudan, Syria,
Pliocene
and Yemen.
turbidites, offshore
He
Nile
is a teaching
Delta.
professor at the
If
American
you have any
University in
questions during the
Cairo,
course of the
Ain Shemesh,
presentation, please feel free
Alexandria,
to
and
click on the
Cairo
box below
universities.
and enter
Dr.
them, and
Brucker
we
will
will
be
address
presenting
them at
today
the
on the
conclusion.
he has 40 years of
Here
experience
is
in the
Dr.
oil and gas
Brucker.
exploration.
Good morning, everybody, and my name is Ali Bakr, and I'm glad to be with you today, and I hope all of you listening are safe and well. My presentation today is titled Application of Unsupervised Machine Learning for 3D Seismic Offshore Nile Delta. It's a simple presentation as a case history in order to show you the application of the unsupervised machine learning in the turbidite in the offshore Nile Delta itself. This is a part of work, of PhD work, belonging to one of my students. This is the shoreline of the Mediterranean to the Nile Delta on the onshore. And West Delta Deep Marine is a concession, was firstly belonged to British Gas. And now it has been acquired 3 years ago by Shell. And the operator of the West Delta Deep is a joint venture company called Rashid El-Burullus Joint Venture. Actually, this concession in a deep water, about 100 kilometers from the shore, and the depth of the water in that concession ranging from 500 to 1,000 meter, from 500 to 1,000 meter, and also the length of the turbidite itself that we are looking for is almost 35 to 40 kilometer length, while the width is again 500 to 1,000 meter width, and the thickness of the sand in here, the reservoir, ranging from 100 meter to 200 meter. This means that it could be resolvable easily by the seismic. This turbidite have been mapped using a conventional way of using the attribute decomposition. But let me first give you an idea about the stratigraphic section belong to this turbidite, and also some idea about the reservoir. Again, this is the shoreline, and this is Egypt, and this line is north-south line. It's a geoseismic line, come from the Nile cone and going to the deeper stuff on the north direction, on that direction, where the range of the West Delta Deep ranging from 500 up to 1,000 meter depths, while to the north it's going more deeper and deeper. The Nile cone here are some very thick sediment for the Pliocene Pliocene, and this section, the Pliocene Pliocene section, you can see it here, and this is the interval of it, and we call it Kafr Sheikh and Wastani. Those are the two main reservoirs that we are looking for. And again, the environmental model is lies, as you can see, where deposit come from the south, and it cross the hinge zone in here, and then it deposit bottom in the bottom on the ocean bottom fans in here, and also it deposits deep marine turbidite channel, and just exactly what we are looking for. Jumping to the seismic, actually the area is covered by 3D seismic of good quality, as you can see in here, and the interpretation started by dividing the section, the geological section, into three sequence boundaries, as you can see, from the seabed to sequence bound 1, and then sequence bound 1 itself, and sequence bound 2, and sequence boundary 3 in there. Our interest is on sequence bounding 3 in here, and there is some little faults that are affected the area, and actually it's not a big thrown. The channel, you can see the channel very pronounced by high amplitude in here in this area. Actually, this channel have been mapped by through the amplitude itself. We are using what we call a triple amplitude. We will see this on the next slide, and have been mapped also by the spectral decomposition, where we three frequencies have been involved and color blending in there. Accordingly, the polygons of this map, using that, have been drawn in the front of you, as you can see it here on the top of the SB3 time map, as you can see it here, where almost the high is toward the south, and as you go to the north, things are going deeper. This little yellow rectangle here represents the area that we selected in order to run and look for the unsupervised machine learning. Why? The reason why, because actually this is, we call it segment 1, and there is segment 2 in here, and there is segment 3 in here for the total length of 40 kilometers almost of the channel itself, because 3 wells have been drilled from out of the 4 wells have been drilled into that part, and we have some good information in order to tie things together. Again, this is a workflow that we use in order to come up with the previous map. We started with the structure mapping on the SB3 itself, and come up with this nice map showing that the high is toward the south. And actually, at the same time, we run the normal procedure, the conventional procedure for the exploration at that area, which is the average amplitude, the average absolute amplitude, and the spectral decomposition. And from those together, we come up with the spectral decomposition display with color blending, and in the other hand, the time map with amplitude posted and the geometry of the channels coming from the spectral decomposition is posted as well. Accordingly, this kind of work have been used in order to come up with the proposal for the wells, and also calculation of the GIIB. Enlarged again, the two main input for the drilling the wells was the color blending for the top sequence boundary 3, and then also the amplitude variation. Something to notice that the amplitude itself within the channel itself is variable. So it's strong, and then it's weaken, and strong again, and strong again, and weaken again, and strong to the south. Something just to keep it in mind while we are looking for this little square. Now that little square or little rectangle, this is a larger part of the segment 1 of the channel itself, where you can see that the location of the 3 well. Something to notice that the amplitude in here is much higher than amplitude in there, and the 3 wells are gas producers. And actually, the P50 about 0.6 TCF or 630 actually BCF exactly on coming out from the using the 3 wells. Now let's switch to what this is fine up to this moment. The 3 wells are producer, and we know they are producer, but now we neglected those 3 wells, and we wanted to look at the unsupervised machine learning, what it will define, how it will define this. Will it define exactly like the spectral decomposition did and amplitude did, or something will happen different? And from that we will drive. So we choose some of the attributes, some of them the spectral decomposition component for geophysical insight, the sweetness, the texture, envelope, and the energy ratio similarity. Actually, those are what we choose out of the PCA. But more than those have been used for the PCA, but out of this PCA, we come up with those are the most infeeding attribute. Then we run the PCA over this four line, and then after that we use the data in order to run our SOM using the PCA result. Doing that, showing you just the images. So this is the spectral magnitude component, then the spectral voice component, and the spectral phase component of the spectral decomposition of Geophysical Insight algorithms. Easily you can check the channel itself. Easily you can pick it up either here or for the magnitude or the voice or even the phase itself. Something interesting on the voice itself, that the isolation of another channel could be there, that can you see it more pronouncedly and more effectively on the voice and maybe the magnitude rather than the phase. We will talk about this next. The attribute also that have been involved according to the BCA result is the energy ratio similarity, the envelope, and the sweetness. So those 6 together, if we consider that the spectral decomposition component are 3, with those 6 together have been used in order to run 10 by 10 maps. To the right, the 10 by 10 SOA maps, and to the left, just 12 neurons out of the 100 neurons in here have been used to identify the channel itself. From this 10 by 10 SOM map, you can see that yes, it's defined very clearly for the channel itself, or the segment one, actually segment 1 of the channel, and the 3 reds. Or in here, the 3 reds are contributing into the position of the point bars sometimes, as you can see it in here. Actually, we didn't like to post the wells in here just to give you the time in order to look at the color without biasing. To the east of this channel, there is something in here. When we isolate the 12 neurons in here, there is another stuff. Look at the effect on the point bars in here, in there, and in there as well. So we have 3 positions: this position, that position, and that position. Now let us see what post the wells looks like. Before posting the wells, actually, I'm going to show you some correlations just to keep in mind how the variation in thickness before posting the well. Those are the 3 wells from south to north, and as you can see, the change from the thickness of the sand ranging from 85 up to 120. There is no big difference on the thickness, but actually there is a difference, about 25% to 30% difference on the thickness. And also the bearing itself, the thickness of the bearing sand itself, also ranging from 90 to 60 in here. So about again 30% different on the thickness and of the sand, and 30% difference on the thickness of the pregnant sand as well. Keep this in mind because we are going to use this on the in the information coming. Let us put those 3 wells on the 10 by 10 map in here, and you can see that the red color is more or less come with the location of the 3 wells. Somebody will say that it's there and it's there. Okay, that's fine, but let us see the next slide where we are going to isolate only the effective neurons or the effective hexagons into that. If you put the same locations of the wells on the spectral decomposition, you cannot differentiate any one of them. And actually, the location of those wells have been selected according to a geological concept rather than using the output of the spectral decomposition itself. Now, jumping to the 12 effective neurons or 12 effective hexagons in here, and this is the location on them. Still, this guy is very bright red, and this guy and that guy also are quite pronouncing and they're quite red, and there is no much difference actually in reality. They are red, yes, but there is no much difference between the 3. This could be directly that the 30% change on the saturation with gas the thickness of the sand saturated of gas, and also the total thickness of the sand as an influence on the change of the neurons that involved in that is not enough. But at least this is very clear that those neurons in here are more or less similar to those one on the channels that have been isolated from the SUM map. Let's come in here to another conclusion. This is again our channel isolated using the 12 only those two neurons, and actually this is the channel, the main channel, and there is another channel in here. This channel, you can see it on the upstream side. This is the downstream side, which is our main channel, and there is another channel actually on the upstream side in here, and this color or these neurons are reflecting the same response that reflected at the 3 wells, may be more higher response on that location. And actually now we are working also in order to isolate and see how this will feed into the exercise itself. The next step that we are actually still running until this moment is to extract this channels using the same method, and after the extraction of this geobody, we are going to run a supervised machine learning using the wells and come up with reserve estimation, and compare that reserve estimation with the reserve estimation that have been used before we are applying some techniques. But actually this is not concluded in here, because actually we are still working. Let us now just conclude what we have received according to this application of unsupervised machine learning using SUM on West Delta deep offshore Nile Delta clearly demonstrate the strike and the geometry of the Pliocene marine turbidite. The southern segment of the channel penetrated with 3 wells are very well defined after posting the wells, as almost similar response from SUM on the neurons hexagons at the location of the 3 wells, which reflect the similarity of the reservoir nature, thickness sand, content, and base thickness as well. Another significant channel is resolved to the east of the main channel, is not detected using the conventional spectral decomposition. Thank you very much, and any questions I'm ready to answer. Thank you.
Thank you, Dr. Bakr. That was fantastic.
You're welcome.
One of the things, if you guys have any questions, please ask them in the chat room. You can access that from the blue button that says Ask Questions right below the video. So, Dr. Bakr, your first question is, hi, why did you choose 12 neurons?
That's a good question. Actually, we started with large number. Actually, started by 10 by 10 on the OSOM to have about 100 neurons. But we find that very details are coming that more or less confuse. Yes.
Fantastic. Another question is, I do not understand why this application is referred to as machine learning. It seems to be a rather straightforward PCA. Could you talk a little bit to which portions are machine learning?
Can you hear me?
Yes, can you hear me?
Yes.
Oh, that question's actually been answered. So are there any other questions? Oh, how many attributes did you input initially into the PCA?
Yes, actually answering the second question, why we did use only 12 neurons, actually because are those the neurons that selected from the 48 neurons, or for the 68 neurons that shows the geometry of the channel.
Fantastic. How many attributes did you input initially into the PCA?
About 18 attributes, 18.
Okay.
And from the PCA, we selected only the 6 attributes.
Okay. How now you know, let's see. Is there a possibility that the newfound channel is the splay deposit associated with the main channel?
I didn't understand the question in reality, but let me tell you that the feeding of the channel is coming from the south, from the river Nile originally, or from the delta, and it crosses the border and it goes into the deep marine. And we expected the normal expectation of deposition of the sand at the point bars, where the channel is bending. This is the most probable part from the channel. It would be rich in sand.
Okay. The next question is on which parameter / output neurons have been trained. For training 3 wells that have been used, can you please clarify?
Absolutely. We didn't use any well at all. Our exercise is unsupervised machine learning. We started from the beginning. We dropped out the wells, but we just started to run a random neurons within the volume of the channel itself, or the seismic volume. And totally the software, the machine learning itself, resolved the channel with the way that I displayed it. And then after that, we put the wells just to see things, but we didn't use any kind of supervision on our exercise. Our next step is to put the wells and use the supervision of the wells for the faces. So we know from the wells where is the sand and where is the shade. We can use this as a supervised machine learning and come up with volumetrics accordingly and compare this volumetric with the other volumetric that we calculated using the normal conventional procedure of the spectral decomposition and the mapping the top and the bottom of the sand. This is a clue of the work itself.
Great, thank you. Okay, your next question is, did you include a pre-stack inversion as part of your data that was examined?
Yes, actually.
Perfect.
We did all the stuff had been done, all the conventional stuff had been done for this data away from the machine learning. We did inversion, we did a pre-stack attribute, we did a post-stack attribute to come up with the final shape of the channel according to the conventional. In contrary, we started to see the machine learning to compare actually what would the machine learning add. So without doing this inversion, if away from the machine learning separately, we don't need to do any inversion, because actually the machine learning come up with a product that directly resolve the channel in the front of us, that directly resolve even the neurons associated with the sand that's pregnant with the gas.
Fantastic. So your next question is, which well has the better reservoir quality? Is it the one to the north or the south of the channel? And can you also isolate the fluid inside the channel with the SOM?
That is one of the hope that we are trying to see, is to separate the neurons that associated with the fluids and started to characterize them. And this is going to be, of course, using the well at the supervision. This is the next step on our workflow, is to look at the signature of the sand, the wet sand, the signature of the sand that's pregnant with gas, and also the signature with the sand that have water on it. And from using this as supervision, we can start for looking better and better resolution. And by the way, the resolution that come from the neuron come up to 10 feet or 12 feet, which high away from the normal resolution of the seismic. We are talking about 30 feet or more than 30 feet, while the resolution in this case is much higher.
Great. Have you used only the AAA or SD map generated in the window specified during the presentation 400 to 450 milliseconds below the SB3 to train the algorithm, or did you use the whole seismic data set?
That's a good question. We used the interval that included SB3. Not everything, actually. We started with the interval that we know the channel is there. Above that interval and below that interval with just a part sub-volume from the seismic. Because actually we are using one of the good laptops with good RAM on it and good working condition in order to run this. It takes time. That's why we selected only the area above and below the zone of interest.
Of course. So there's one question I think I accidentally missed. So they wanted to know, have you been able to identify the new channel on the traditional attributes at all?
The answer is partially yes, but not to the limits of the of application of the machine learning. The machine learning bring it in a very clear way than the conventional way.
Fantastic. Are there any more questions? Yes. Okay. So do the channels feed the submarine fans?
We believe so. Because actually we didn't drill on the submarine fans. It's too deep over there. As you go, the depths of the water reach almost 3,000 meters, and the drilling over it is very costly. So we are restrict our work on the Pliocene, Pleistocene on the depths that ranging between 500 to 1,000 because of the expensive well over there.
Great. We'll give them another minute to ask any more questions.
Sure.
Okay, that seems to be all the questions that are coming in for now.
That's fine.
So thank you for presenting. It was a great presentation, and thank you everyone for attending.
Thank you. Yeah, thank you.
There will be another presentation back in the auditorium at 10 a.m. from Jacques Fock, the Chief Innovation and Digitization from OMV. So that will be at 10 a.m. in the auditorium.
Okay.
Thank you so much.
Bye-bye.
Goodbye.